Hi everybody, I hope that all of you are doing well. Today we will do lab number 3, and in lab number 3 we will study Kirchhoff's laws. So we will study Kirchhoff's law that is related to current, and Kirchhoff's law that's related to the volt. What we will need in today's experiment, so we will need power supply 12 volt DC. We will need the voltmeter to measure the volt, and then we will need some resistors. Actually, since we don't have resistors, you know from the last lab that we used these bulbs as resistance. So here this bulb has a resistance 37.6 ohms, and this bulb has resistance 46 ohms, and this bulb has resistance 44 ohms. So this is everything that we need for today's experiment. Let's get started and start step number 1, which is studying Kirchhoff's law that's related to voltage. Hi everybody, let's start today's experiment. So as I mentioned, we will study Kirchhoff's laws, and we will start with Kirchhoff's current law. So this part, guys, will be the second part. Actually, we will start with Kirchhoff's voltage law, but I prefer to explain Kirchhoff's current law because this law is Kirchhoff's first law. So I will explain it and then explain Kirchhoff's voltage law, and then when we start the experiment we will start working on Kirchhoff's voltage law. So as you can see here, so for any node in an electric circuit, the sum of currents flowing into that node is equal to the sum of currents flowing out of that node. So this is actually definition for Kirchhoff's current law. And here's another definition, guys. So the algebraic sum of currents in a network of conductors meeting at a point is 0. So as you can see here, guys, in this figure, we have current go through this resistance, and it is I0, and once this current achieves this point, it will be divided into 3 currents, I1, I2, I3. So when we apply Kirchhoff's first law, we will notice that I0 is equal to I1 plus I2 plus I3, and I0 minus I1 minus I2 minus I3 is equal to 0. So this is actually Kirchhoff's first law, and what we are going to do now, guys, we will move to explain Kirchhoff's second law. So let's move to Kirchhoff's second law here. So this is Kirchhoff's second law, and as you can see, we can call it Kirchhoff's voltage law. So here we can see definition for Kirchhoff's voltage law. It states that the direct sum of the potential differences, which are the voltages, around any closed loop is 0. So here we have this circuit, as you can see. We have power supply here, we have R1, R2, R3. So when we measure the voltages, VR1 across R1, VR2 across R2, and VR3 across R3, and then sum them up, and then subtract them from the power supply voltage, we should have 0, according to Kirchhoff's second law. So this is the theoretical, guys, behind, or the background behind today's experiment. So simply we will start with Kirchhoff's second law, and then we will do Kirchhoff's current law. And these are the quantities that we are working for. So actually what we will do, so we will start with connecting this circuit. So it has R1 37.6 ohms, R2 46 ohms, R3 44 ohms. And then here we have power supply, and this power supply is a 24 volt DC. What we are going to do, guys, we are going to measure the voltage across R1, R2, R3, so that will give us V1, V2, V3. And then we are going to find the current, and just check that the current should be the same here. So we'll divide V1 over R1, V2 over R2, and V3 over R3. Here we are applying Ohm's law. Perfect. And then we need to make sure that Kirchhoff's second law is working well here with our circuit here. So what we will do, we will subtract V1, V2, V3 from VP and see the result here. And then the second part would be connecting this circuit that you can see here. So here, as you can see in the first part, we have those resistors in series, but here we will have those resistors in parallel. And what we will do here, guys, we can see here that we have R1, R2, R3, the same resistors, just in order. And what we are going to do, guys, we are going to measure V1, which is the voltage across R1, V2, voltage across R2, V3, voltage across R3. And then we are going to figure out V1, 2, 3, which is the voltage across all of these resistors together. Actually, it is the voltage across the equivalent resistance. And then find the current here, guys. So this is the current that flow in the circuit. It's equal to V1, 2, 3 divided by R equivalent. Actually, last experiment, or when we did last lab, we evaluated R equivalent. So then we will get the current here. And what we are going to do also, guys, we are going to find I1, I2, I3, because according to Kirchhoff's first law, each one of these resistors experience different current. And then finally, guys, we will end up with checking if Kirchhoff's second law works very well with this circuit. So what we will do, we will subtract I1, I2, I3 from I total here and see if we can get 0 here. So this is today's experiment, guys. So we'll have two parts as I explained. So let's get started and move to step number 1, which is connecting those bulbs. So here, instead of having real resistors, what do we have here? We have bulbs. And explain that they still have kind of resistance. So it's a good idea to use them, and it's very safe. So there is no problem with using them. And here we have 24 volt DC power supply, and also we have the voltmeter to measure the volt. And all of these resistors are connected in parallel. In series. So they are connected in series. Actually, this circuit, just to double check with you guys, this circuit is the same as this circuit. So now we are going to measure the quantities that we are looking for. And the first thing that we will do, guys, we will connect the circuit. So let's do that together. So I will connect the circuit, so right here, and the other side should be connected to the power supply. So the first thing that we will do here, so I will keep the voltmeter here in front of you so you can see what do we have. So what I will do, guys, the first thing that I will do, I will measure the voltage across the power supply. So let's do that. The voltage across the power supply. It's a good idea maybe to go from here. Yep, so let's see what do we have here. So it's not stable. Maybe we can just connect it directly to the voltmeter. So that can work better. So let's do that. And as you can see here, guys, this is the voltage. It is minus here because I need to reverse the terminals. So that's totally fine. Don't care about this minus sign. But here we have 24.1 voltage. So this is the power supply voltage, and we will write it here. So it's equal to 24.1 volt. This is the power supply volt. So that's great. I will write down here VP, so we know that we are writing VP here. So that's great. We can also try to highlight it, but I don't have a highlighter right now, so that's totally fine. So we know that the power supply voltage is 24.1 volt. So that's great. Now we need to disconnect the voltmeter like this, as you can see, guys, and then connect the power supply to these resistors here. So let's do that. So connect the power supply. So that's great. And then, guys, I'm going to measure the voltage across our number 1, and let's see what do we have. So I will measure it right now, gently and slowly, and see what do we have. So we have, as you can see here, we have 8.6 volt. So this is the voltage across resistance number 1. So let's write that down, guys. So we have 8.6. So that's great. So V1 is equal to 8.6 volt. So this is V1, guys, 8.6 volt. This is the voltage across R1 that has 37.6 ohms. So now we are going to measure R2 across R2, and let's see what do we have. So let's do that also gently and slowly. Try to do that. So what do we have here? Let's double check. We have 8 voltage. The voltage is 8 volts. 8 volts. Let's double check again. So what do we have? We have 8 volt. Great. So now we know the voltage across R2. So it is 8 volt. So what do we have here? We have 8 volt. So the voltage across R2, which is 46 ohms, is 8 volt. So that's great. Now, guys, we will move to the next one, which is V3, the voltage across R3, which is 44. Let's see what do we have here. So across, okay, 44. Let's now do that gently and slowly. So what do we have? We have 7.8 volt. Let's double check. We have 7.8 volt. So that's great. Let's write it down, guys. So V3 is equal to 7.8 volt. So that's great. I will just double check and see. So this is 44. Yep, that's correct. Double check this resistance, 46. That's correct. Yep. So here we have V3 is equal to 7.8 volt, and it is across resistance 44 ohms. Now guys, I will go through these and see what do we have. Let's calculate the current here. Let's calculate the current. So the current should be the same. So the current here should be the same. I will just look for a calculator. I have calculator here somewhere. I will bring the calculator and then come back. Okay, apologize for the delay, but we can continue now. So we have the calculator. So what do we need to do, guys, right now? So we need to divide V1, which is 8.6, by R1, which is 37.6, and see what do we have. So let's do that. But before this, let's disconnect the circuit here, so that's safer. Great. So let's do that. So the first one, so what do we have here? So here's the calculator. So what do we have? We have 8.6 divided by R1, which is 37.6, and that's equal to. So what I have here, I have 0.23, or we can write 0.229. Let's be more precise. So let's write 0.229 ampere. So that's great. Let's now move to the next one, guys. So we calculated this. So we noticed that the current is 0.229. Now we are going to do this, which is V2, 8 volt, divided by 46 ohms. And let's see what do we have. Okay. Let's do that, guys, here together. So we have 8 divided by 46 ohms. 46 ohms, and that's equal to 0.179. It's equal to 174. So don't worry, guys, if if there's like small difference. So that's fine, because you are doing experiment, and this experiment has lots of some error, not lots of error, but some error, and that can decrease or increase the current. So that's totally fine. So what we have here, we have 0.174. So let's write that down. So here we have 0.174 ampere. Great. So here we have 0.174 ampere. It looks like close. So that's totally fine, even if there is like small difference. Now, what we are going to do, guys, we are going to divide 7.8 by 44 to get this current here, and we will see if we have the same value. So let's do that. So what we have here, so we have 7.8 divided by 44, so that's equal to 1.77 ampere. So that's equal to 0.177 ampere. Sorry, so 0.177 ampere. Yeah. So you can see here, guys, the current is approximately the same. There is small difference here, and the reason, we don't have perfect circuit here. So what I did here, I did my best to have like good components for this circuit. But even though, look at, we got nice results here. So the current approximately 0.2, 0.2, 0.2. So we can write here 0.2 ampere, and here 0.2 ampere, and here we have 0.2 ampere. So we can write that. So that's approximately 0.2 ampere, 0.2 ampere, and 0.2 ampere. So that's great, guys. Now we are going to check if Kirchhoff's second law works very well with this circuit. So what we will do 24.1 minus 8.6 minus 8 minus 7.8 is equal to, and we should have 0 here. So it should be 0 here, but we will see what we will have here. So we'll write that. So that's equal to 24.1 volt minus 8.6 volt minus 8 volt minus 7.8 volt, and that's equal to. So let's see, what do we have? We have 24.1 volt, which is the power supply voltage, minus 8.6 volt, which is the voltage across R1, and then we have 8 volt, which is the voltage across R2, and then we have 7.8 volt, which is the voltage across R3. Now let's calculate that, guys, and see what do we have here. So what we will do here, we will go to the calculator and do that together. So we have 24.1 minus 8.6 minus 8 minus 7.8. That's equal to. So what we got here, we got minus 0.3. So that's fine, guys, because we are doing experiment. It is approximately 0. It's a small number. And we have 0.3 here instead of 0 because we are dealing with a circuit that has kind of error here. It has error. But that's fine, guys. So I consider this result perfect result comparing to what we did here. So let's just double check if the result is correct here. So we have 24.1 minus 8.6 minus 8 minus 7.8. That's equal to minus 0.3. So let's write that down here. We have minus 0.3. Yeah, so this is the final result here, guys, and we can see that our circuit that we used is acceptable and it is good. And actually we did nice experiment here, and we made sure that Kirchhoff's second law works very well with this circuit, and we proved it right now. So this is part number 1. We will do now part number 2. Let's do that together, guys. This is step number 2, guys. what you can see here, you can see the bulbs or the resistors are connected in parallel. So resistor number 1, 2, 3, and all of them are connected in parallel, similar to this circuit that you see here. So we have R1, R2, R3 connected in parallel and connected to the power supply here in series. So we will start with the power supply. So as you can see here, guys, the power supply has voltage 6.38 volt. This is DC volt. So let's write it down. So V power supply is equal to 6.38 volt. So this is the power supply volt. So that's great, guys. What I'm going to do now, I'm going to measure the voltage V1 across R1, and then V2 across R2, and then V3 across R3. And then, guys, we will try to calculate I1, I2, I3. So according to Kirchhoff's first law, we know that the current I here will split to 3 currents here after this node. So we need to make sure that or we need to just double check that Kirchhoff's second law goes very well with our circuit here. So to make sure if this circuit is correct and Kirchhoff's first law works very well, we need to go through this equation. So we need to subtract I1, I2, I3 from I here. And I, guys, can be calculated from V123 divided by E equivalent. So what is V123 here? The V123 here, the voltage across these 2 points here. Or we can say that the voltage across the equivalent resistance. We measured the equivalent resistance last session, and it was 14.07 ohm. So this is the equivalent resistance for these 3 resistors that are connected in parallel. So this is great. So we have everything, guys. The only thing that you are missing is measuring these voltages here. So let's do that, guys, together. So the first thing that I will do now, of course, I will use the voltmeter to measure the voltage. But the first thing that I will do, I will make sure that the connections are working very well here and everything is connected. So that's great. Now I will connect the power supply to those resistors, as you can see, guys, here. And then we need to measure the voltage. So everything is connected here. Now we have 3 resistors in parallel with the power supply, which is 6.38 volt. So what I will do now, I will measure the voltage across R1, the voltage across R2, the voltage across R3, and then measure the voltage which is across the equivalent resistance, which is VR123. And let's see if that can support Kirchhoff's first law. So let's do that together, guys. Keep watching the voltmeter here. So I will do that right now. This is the first resistance here. So what we have, oops, let's do that again. We have 6.09. 6.09. This is the voltage across resistance number 1. So we have 6.09. Let's write that down. So 6.09 volt. I will write it down here. Just a minute, guys. So we have 6.09 volt. Yes, so this is the voltage. This is the voltage, 6.09 volt across R number 1. So now I will measure V2 across R number 2. So let's do that. We need to have those terminals here and then measure the voltage here and see what do we have. I think this one needs to be measured carefully. Maybe I can do like this. Let's try again. Sometimes it is hard to measure everything from the first time. So what I will do, guys, I will make sure again that everything is connected. I will make sure that everything is connected. Great. So now I will measure the voltage here. So what we have here across this resistance is 6.03. You can see that here on the voltmeter. I will double check again. So we have 6.0302, 6.02. We have 6.02. Okay. So V2 is equal to 6.02 volt. So this is the voltage. This is the voltage across resistance number 2. Let's now move to number 3 and measure the voltage here and see what do we have. So I will do the same thing, just try to be precise as much as I can. Oops. Still not connected very well, so I need to make sure that everything was connected here. Try to measure again. So it's 5.98. I will double check the connections here again, just to make sure that everything is going well. So what we have 6.02, 5.97, 6.01. Oops, I need to keep everything here fixed. Yeah, so this is what do we have. I think we have 5.99. Double check the connections again. Oops. Double check the connections. It is hard sometimes to measure. Yeah. I will try again. Yeah, so I think we have 5.95. 5.95. Yeah, let's double check here for R2 and see if there is any difference here. Yeah, what I believe that the voltage of the power supply like went down maybe. Yeah, it went down here. It became 5.95. So yeah, we can consider the 6 voltage. I think you have seen here 6.1. If we go back in this video, you will notice that we got 6.1. So this 6.1 was before the power supply voltage went down. So I will consider the 6.1. So that's fine, guys. So that's okay. So from this we got 6.1, and I believe you have seen that. You can go back in this video and watch the process of measuring the voltage across this resistance, and you will notice that we got 6.01 here. So V3 was 6.01 volt. So the reason was that the power supply here go down because we are using batteries here, and the batteries will go down. When you use them, they will just, the voltage will drop down. But I think we measured those voltages fast enough to get correct measurements. So that's okay. So now, guys, as you can see here, so the power supply was 6.38 volt. We can see that the voltage across R1 was 6.09, across R2 was 6.02, across R3 was 6.01. So that's fine. And also, guys, across the equivalent resistance should be one of them. So we can use one of them because according to Kirchhoff's first law, the voltage should be the same. If we measure the voltage from here, from here, from here, from here, so we should have the same voltage. So we will try to calculate I first, which is the current that flows in this circuit. So it should be 6.02, let's choose 6.02, divided by our equivalent. And our equivalent, guys, for these resistors is 14.07 ohm. So we have 14.07 ohm, and that will give us, so let's calculate this first and then show you guys what we got. So let's do that. So we have 6.02 divided by 14.07. So what we have 0.427 ampere. So this is the current that we have here. So it is 0.427 ampere. So that's great. Now, guys, we need to go here and measure the current here. We need to measure the current across R1, R2, and R3. And let's see what do we have here. So we have the voltage, so we have 6.09 divided by R1, 44 ohm, and then we have V2, 6.02 divided by so R1 is 37, so R1 is 37.6 ohm, and R2 is 44 ohms, and V3 is 6.01 divided by R3, which is 46 ohms. So now we have all of them here, guys. So we figured out the current that flow in this circuit. So it is 0.427 ampere. So this is great. Now I'm going to calculate I1, I2, and I3. So let's do that together. I'll write the answers here. So I1, let's do that together. So I1, guys, should be 6.09 divided by 37.6. So that's equal to 0.62 ampere. So you have 0.62 ampere. So I1 is equal to 0.162 ampere. Now let's see I2. Let's see I2. So I2, guys, should be 6.02 divided by 44, which is it should be our yeah, it should be 46. It should be 46 here. I will erase 44 here, so that's wrong. It should be, so here we need to have 46 ohm, and with R3 we need to have 44. Yeah, so this is the correction that I did. So R2 is 46, you can see that, and R3 is 44. So this is what I did. And you can check from here, guys. So yeah, I believe R3 here is 44 and R2 is 46 ohms, and here is R1 37.6 ohms. Yep, so this is correct. Now let's continue calculating the current. So let's do now I2. So we have 6.02 divided by 46. So that's equal to 0.13. It's equal to 0.13 ampere. So I2 is equal to 0.13 ampere. Now let's do this, guys, and figure out I3. So I3 can be calculated from 6.01 divided by 44. So that will give us 0.136. So we can say 137. So that's fine. So it's equal to so I3 is equal to 0.137 ampere. So this is what we have, guys. Now what we need to do, we need to make sure that Kirchhoff's first law is working by applying this equation. So I1 minus I2 minus I3 minus I2 minus I3 should be 0. So this is what we will do right now. We will make sure that this equation is valid. So let's do that, guys. So here we have 0.4, sorry, so we have 0.427 ampere minus 0.162 ampere minus 0.13 ampere minus 0.137 ampere. So this should equal 0. We will make sure if this is equal to 0. So this equation is equal to 0.427 ampere minus 0.162 ampere minus 0.13 ampere minus 0.137 ampere. Let's see, what do we have? This value should be 0. So let's calculate that together. So here is my calculator. and we will do that together, guys. So we have 4, 0.4, it should be 0.4 to 7 minus 0.162 minus 0.13 is equal to minus 0.137. I think I made a mistake here. We should do that again. So let's do that again. So we have 0.427. So this is good. Minus 0.162. So that's equal to minus 0.13, 0.13, that's equal to, and then finally minus 0.137, so that's equal to. Yeah, this is what we got, guys. Perfect. Perfect. So from this circuit we could manage to prove that Kirchhoff's first law is correct. Yeah, and this is actually the main purpose of this experiment, is to prove that Kirchhoff's first law and Kirchhoff's second law are correct and they are working. And you learned something, guys. You learned, guys, when you connect the resistors in parallel, you can see that you will have the same voltage across each one of the resistors. If you connected them in series, you will notice that the voltage is different, but the current that flows in this circuit is the same. So this is in series. Yep, guys. And what we have here, we have those resistors connected in parallel, which is this. Just to go through what I said again. So here in this circuit we can see that we have different currents, but the voltage is the same. Here we have different voltages, but the current that flow in this circuit is the same. And we proved Kirchhoff's laws, the first law and the second law. I will write that down here. So what we got minus 0.002. So this is what we got, I believe. Yes, this is what we got, minus 0.002. It can be positive number, it can be negative number, but the most important thing, it should be very small. And it is very small here. We have 0.002. Here, with Kirchhoff's second law, we got 0.3, so that's fine, because we have error in this circuit, and also here we have error, but the error here is small and the error here is a little bit big. But in general, we have everything, guys. I will of course send you the worksheet so you can finish today's lab. And the most important thing, you need to watch the video, and after you watch the video you can finish the worksheet. Or you can finish the worksheet while you are watching the video. So that's fine. Thank you so much, guys, and see you next lab.